All right, welcome Math 1111ers to Lecture 1.8. I'm going to leave my video off because I'm at home and I tend to have bandwidth issues if I play my video, and y'all probably don't want to see me anyway. It's a snow day. I hope y'all are enjoying yourselves and staying safe and warm. So 1.8 is all about inverse functions. And so we're going to go ahead, and I apologize for the fuzziness. Once again, I take screenshots of the note sheets and put them onto the PowerPoint slide. So that's why there's the little Word document green line there telling me there's a spelling or a grammatical error, and it's because there's a blank in the sentence and it's very fuzzy looking. So pre-apologize. Hopefully you're following along with the PDFs that I post in the content area of D2L. Okay, so let's first start by talking about the definition of an inverse function. We have inverse functions, and let's go back to think about inverse operations. So inverse operations are operations that, one easy way of putting it is they undo each other. So for example, addition and subtraction are inverse operations. Multiplication and division are inverse operations. Squaring something and taking the square root are inverse operations. And actually, let's take a look at squaring and taking the square root, because there's something that comes out of looking at these that's very important. So if I start out with a variable x, if I square that variable, it looks like x squared. Now, if I come back and take the square root, remember the understood index there is 2. If I take the square root of that thing that's squared, I end up where I started, at x. So that's what we mean when we say they undo each other. They unpack the boxes. So once again, if we start with x, if I add 3, and the inverse operation would be subtraction, so I'd subtract 3 as well, and I end back up at x. Okay, so there are a few different ways to identify inverses. One we talked about when we, in the section that we talked about transformations of functions, and we saw that inverse functions, XY tables were exactly opposite of each other. So let me give you a quick example of that as well. So for example, if we have x cubed and the cube root of x, let's say that this is f of x here, and this is g of x here. If I made an f of x table, 0 cubed, actually let's start in the negatives with that. Let's say -2, -1, and I'll erase this in a second, 0, 1, and 2. I have no idea why I'm going uphill like this today. And we'll take a look at the x, g of x table as well. -2 cubed is -8, -1 cubed is -1, 0 cubed is 0, 1 cubed is 1, and 2 cubed is 8. Now if I come over here to my g of x function, I'm going to choose these values so that they are perfect cubes. The cube root of -8 is -2. The cube root of -1 is -1. The cube root of 0, 0. Cube root of 1 is 1. Cube root of 8 is 2. So what I would like to point out here is that with inverse operations, and I'm telling you, and I'll show you later, or verify to you that these are inverse operations, but I'm telling you that these are inverse operations. They undo each other. So you should notice that their f of x tables are exactly flip-flopped from each other. So that's one way of telling if functions are inverses of each other, is to look at their x, y tables. All right. So going back to just the idea of undoing each other, that's where we get this definition here. And this definition is the way that we actually verify if two functions are inverses of each other. So what has to happen is you have these two functions, you're trying to figure out if they're inverses. You compose the functions both ways. So f composed with g, where f is your shell and you're plugging in the g function in for x. And you compose it g of f, which g is your shell, f is your plug-in. Both times you do these compositions, you have to end up with just x, just like we did with the cube root and x cubed. I undid them and ended up with just x. And what this means is that for every x in the domain of g and for every x in the domain of f, this is true. So the function g, once I verify, when I compose both ways, I can then call g the inverse of f or vice versa. So the function g is the inverse of the function f and is denoted by, well, we have this notation here. Now this is not f raised to the negative first power. This is the notation that we have for the inverse function. So if f is our given function, if I figure out that another function is its inverse, I can rename that function f inverse. So I could replace the wording here with g and f and say that f composed with f inverse has to equal x, and f inverse composed with f has to equal x. The domain of f is equal to the range of f inverse. That's where you see the flip-flop of the tables happen, and vice versa. So, moral of the story is, to verify that two functions are inverses of each other, simply compose the functions both ways and see if both compositions yield x. So this little picture over here is in your notes, and this is just a visual of what I'm going to be doing off to the right-hand side here. I'm going to show you that the functions f of x and g of x are inverses of each other. So I'm about to compose them both ways. The first composition that I'll do, let me color code this so that it's easier to see. I'll make f of x red, and I will make the g of x function green. Okay, so the first composition that I'm going to do is f composed with g, which means that my f of x is going to be my shell function, and I'm going to plug in my g of x function wherever I see f within the function. So this is what that looks like. My f function is 3x plus 2. So I write 3. I don't write x. That's where I'm going to plug in the other function, plus 2. And this is how it looks when I plug the g of x in, x minus 2 over 3. Okay, so now I'm just going to start simplifying this expression here. Well, 3 divided by 3 is 1. So at this point, I'm left with x minus 2 plus 2. There is an understood positive 1 that gets distributed there. So I have x minus 2 plus 2. Well, negative 2 and positive 2 are opposites, and I end up with x. However, I cannot call these function inverses yet. It has to compose the opposite way and also give you x. So this time I'm going to do g composed with f of x, which is going to look like this. G will now be my shell function, and I'm going to plug in f of x. So this is what that looks like. I have something minus 2 all divided by 3, and that something is my f of x function, which is 3x plus 2. Once again, to point out, there's an understood positive 1 that gets distributed over the terms inside that parentheses, those sets of parentheses. So 3x plus 2 minus 2 over 3. So positive 2 and negative 2 are opposites, and I'm left with 3x divided by 3. 3 divided by 3 is 1, and I'm left with x. Now that they have composed both ways, and I got x both times, it is now that I can say these functions are inverses of each other. So at this point, since I called the red function f of x, I can call the green function now, instead of calling it g of x, I can say that f inverse of x is equal to x minus 2 over 3. So that's how you have to verify inverse functions. You have to compose them both ways and get x both times. If it only works with one of them, these functions are not inverses of each other. And only when you have verified that you get x both ways can you then rename one of the functions as the inverse of the other. Now, I could have also called the red function g inverse of x and used g of x as my beginning function. It goes both ways there. So hopefully, since I don't have anybody in the room today, hopefully that makes sense to everybody out in virtual land. I'm going to go ahead and move on. Okay, so this is just another example of verifying that two functions are inverses of each other. So I'll make my f of x blue, and I will make my g of x this pinky purple color. Okay, so to begin verifying, I'm going to start with f composed with g, which means that f of x is my shell function, and I'm going to plug in g of x, and this is what that looks like. My shell function is 4x minus 7, so 4, I don't write x, minus 7, and I plug in my other function, g of x, in 4x into the first function. Okay, so 4 divided by 4 is just 1, and I'm left with x plus 7 minus 7. Understood positive 1 in front of these parentheses that gets distributed. And that's x plus 7 minus 7. I have opposites there, and I end up with x. So I'm halfway done. Now I need to compose G with F. So G is now my shell function, and F is my plug-in. Continuing on, I have something plus 7 divided by 4, and that something is my f of x function, which is 4x minus 7. Almost didn't leave myself enough room to write that in there. All right, so understood 1 gets distributed. So I have 4x minus 7 plus 7 over 4. I have opposites here. 4x divided by 4 leaves me with x. I have now verified that my functions are inverses of each other. So if f of x is 4x minus 7, then f inverse of x is x plus 7 divided by 4. Or I could have written that g of x is x plus 7 divided by 4, and g inverse of x is 4x minus 7. It doesn't matter which way you write it, but be careful and make sure when you're doing your homework in My Math Lab that you're giving them the answer that they want. They will tell you what f of x is, and then you will be finding f inverse of x or verifying it. Okay, so that's if you're given two functions and ask if they're inverses of each other. You do the verification by composing both ways. Now, a lot of times you're going to be given a function f of x and you're going to be asked to find the inverse. So these are the steps that you go through to find the inverse of a function. The first thing you're going to do is replace f of x with y. It just makes it easier on the eyes. And then if you remember what I said a little while ago, the x, y tables of inverses are exactly flip-flopped from each other. So the second step in this process is to interchange x and y. You're just going to flip-flop x and y, and I'll show you what I mean there in a moment. Then you solve for y. If this equation does not define y as a function of x, the function f does not have an inverse function and the procedure ends there. If the equation does define y as a function of x, the function f has an inverse function. If f has an inverse function, replace y in step 3 with f inverse of x. Verify your results by composing both ways. Okay, so let's see this process with f of x equals 2x plus 7. So this is my f of x, and I'm looking for f inverse of x. The first step in this process is to replace f of x with y. So y equals 2x plus 7. The next step is to flip-flop x and y. So this is what that looks like. X equals 2y plus 7. And then my last step is to solve for y. So I'm just going to first subtract 7 from both sides. And I get x minus 7 equals 2y. Divide both sides by 2. And since y is defined in terms of x, in other words, I get only one and only one y value for every x value put in, then I have found the inverse. So I rename this f inverse of x equals x minus 7 over 2. So I'm going to make this one that pinky purple color. And now I need to verify, and this is just to make sure that the work that I've done is correct. So f composed with g. My f is my shell, so 2 times something plus 7. And I'm going to plug in my f inverse for x, x minus 7 divided by 2. My 2's divide out, and I'm left with x minus 7 plus 7. Distribute the understood positive 1 into my parentheses. X minus 7 plus 7, and I'm left with x there. So it checks out the first way. I still need to check out the second way, g composed with f. So my g function is now my shell function, something minus 7 divided by 2. The something is 2x plus 7. Understood 1 distributes, and I have 2x plus 7 minus 7 over 2. Opposites right there, 2x over 2, divide out, and I'm left with x. I have verified, so sure enough, I found the inverse function there. Okay, so this one's a little more challenging here. Find the inverse of 3 over x minus 1. So we're given this f of x, which I'll make blue. All right, so I'm just going to take it through those steps again. The first thing to do is replace f of x with y. So y equals 3 over x minus 1. And now I need to solve for y. I'm sorry, I've got to flip-flop my x and my y first. X equals 3 over y minus 1. Okay, now I'm ready to solve for x, or solve for y. Add 1 to both sides. X plus 1 equals 3 over y. I got to get that y out of the denominator, so I need to multiply both sides by y. Here's what I have so far. Y times, sorry, my pen is acting up again. That's the first time with this one, this session. Not too bad. Y times x plus 1 equals 3. Now I need to get that x plus 1 off of there. So I have y equals 3 over x plus 1. Sure enough, for any value that I place into the function for x, I get one value of y out. So I'm free to say that f inverse of x is 3 over x plus 1. I'm ready to verify. F composed with g. Or I could say, instead of saying g, I could say f composed with f inverse. And that looks like this. 3 over something minus 1. I had to leave myself quite a bit of room, and I've actually got a compound fraction happening here. Don't let the F word scare you. So just to point out, this is really 3 over 1 divided by 3 over x plus 1. I never divide fractions. I multiply by the reciprocal. So I have 3 over 1 times x plus 1 over 3 minus 1. My 3's divide out. And that leaves me with x plus 1 minus 1. There's an understood 1 that gets distributed. So x plus 1 minus 1, positive 1, negative 1 are opposites, and I'm left with x. Now I need to try f inverse composed with f. So the exact opposite. 3 divided by something plus 1. Plugging in f for that something, 3 over x minus 1. There's an understood positive 1 that gets distributed. And I have 3 over 3 divided by x minus 1 plus 1. Well, negative 1 and positive 1 are opposites. So I am brought here, 3 over x. Just as a reminder, that 3 in the numerator is being divided by 1, so I'm in the same situation where I'm ready to multiply by the reciprocal. So 3 over 1 times x over 3. My 3's divide out, and I'm left with x. So I have verified that I found the correct inverse function of f of x. So I can then call it f inverse of x. Okay, the next thing that you encounter in this particular section is the idea of a one-to-one function. And a one-to-one function is a function that only has one input for each output variable. So it's sort of the opposite of the definition of a function. So just to give you an idea, the parabola is not a one-to-one function because notice I have two output variables or two output values of 4 there. So that brings us to this idea of a horizontal line test. And what the horizontal line test tells us is that if a horizontal line passes through more than one point on a function, this function is not one-to-one, and its inverse is not does not have an inverse function. So the parabola does not have an inverse function. And we can see that here. It does not pass the horizontal line test. Let me give you an example of something that does pass the horizontal line test. So let's look at the cubic function. So the cubic sort of looks like this. And if I go and put a horizontal line anywhere on that function, it only passes through one point, which means the cubic function has an inverse function itself. And the cubic function's inverse is the cube root function. So it looks like this. Trying to get a different color here. The cube root function kind of looks like this. And we'll see in just a minute, another characteristic of inverse functions is that they reflect across the line y equals x, the identity line. So you can see that the cube root and the cubic function do reflect across that line. And the cubic and the cube root both pass the horizontal line test, saying that their inverse is a function. All right. So this should be super easy. You just want to see which graphs represent functions that have inverse functions. Well, I'm just going to do the horizontal line test. So since the line here passes the horizontal line test, yes, this function has an inverse function. Well, B is a parabola, so no, it does not pass. C, no. And D looks like a version of the cubic, and yes, its function does have an inverse function. Okay, the last concept is the concept that I just showed you about how a function and its inverse will, when graphed, will reflect across the line, y equals x. So that dotted red line going through here is the identity line, y equals x. Notice that this diagram also tells you if the point AB exists on the function f, then the point BA has to exist on the function f inverse. That's the x, y tables being flip-flopped. So if you're given a random graph like we have off to the right here, and you're asked to graph the inverse, what you're going to do is choose some key points, and they've actually shown you which key points to use in this example. And you're going to flip-flop them, graph the inverse, and then you can even graph the line y equals x just to show that it reflects across there. So I'll do the x f of x table here in blue, and like I said, I'm already given my points, my key points to use. So I've got -3, -2, -1, 0, and 4, 2. So my f, or my x, f inverse of x has to have the flip-flop points. So -2, -3, 0, -1, and 2, 4. I'm going to go ahead, let me clean this graph off here real quick, and then I'll graph it for you. And this is our last slide. So the point -2, -3 lives here. Then I've got the point 0, -1, and the point 2, 4. So this is what my graph looks like. And if I came back and graphed the identity function, y equals x, it comes through here and mirrors each side over that identity line. And those are all the concepts that are addressed in 1.8 on inverses. It's a very important concept to have. Unit 3 homework and quiz due Monday, February the 24th. That covers 1.7, 1.8, and 1.9. Quiz will be open on next Thursday, not this Thursday coming up, but next Thursday, which is the 20th of February at 12 a.m. It will remain open through Monday the 24th at 11:59 p.m. And the next lecture over 1.9 will be this next Monday, February the 17th at 3 o'clock. I hope to have everybody join us if you can, and everyone stay safe and warm and enjoy your snow day. Thank you.